We've looked at how to solve equations involving absolute value. Now we're going to look at how we solve inequalities when there's an absolute value involved on one side or another of the inequality. As with other inequalities, absolute value inequalities typically have solutions that are intervals or unions of intervals. However, they require a little bit of work. Our first step is going to be to translate our absolute value inequality into a compound inequality or a collection of inequalities that don't have absolute values in them so that we can use our previous methods of working with it. So let's consider an absolute value inequality like the following. Let's consider a simple inequality. The absolute value of x is less than 5. Now, a solution to this inequality will be a number x where the absolute value of x is less than 5. Now, remember that the absolute value of a number is the distance between that number and 0 on the number line, which means to say that the absolute value of x is less than or equal to 5 is the same thing as saying that x is less than 5 units away from 0 on the number line. So if we look at the number line and we mark where 5 and -5 are, then for x to be a solution to this inequality, it could be numbers that are small and are up to 5 units away from 0. So we're going to get an interval of this form. Now, in this example, 5 and -5 won't be included because a number will be a solution to this inequality only if it is less than 5 units away from 0. And 5 and -5 are both exactly 5 units away, so they don't qualify. So notice that we have another way of expressing this same inequality. We looked at inequalities that had solutions that looked like this back when we looked at compound inequalities. This interval describes the same set of numbers as the inequality x is greater than -5 and less than 5. So this is what is going to give us the translation for absolute value inequalities of this form, where the absolute value of a number is less than some number. So the fact that we're going to use to solve these kinds of problems is the following. The absolute value of a is less than k is equivalent to writing a is less than k and greater than -k. And if we have a weak inequality, if the absolute value of a is less than or equal to k, this is equivalent to -k is less than or equal to a is less than or equal to k. Now, in both of these cases, this really only makes sense when k is positive or 0. If k is negative, then these statements will never be true. So absolute value of a less than k and absolute value of a are less than or equal to k are both I should say have no solutions if k is less than 0, if k is negative. And this is because the absolute value of a number is always at least 0. And so if I said something like the absolute value of x is less than -2, well, that's just never going to be the case. This has no solution. But when k is non-negative, when k is 0 or positive, then the inequalities with the absolute value less than the number can be translated into compound inequalities in this way. So let's do an example. Let's solve the inequality. The absolute value of 3x plus 2 is less than or equal to 7. Well, whenever you run into a situation like this, the absolute value of something is less than or equal to 7, or less than a number, then we can translate it in the way that we just talked about. 3x plus 2 is less than or equal to 7 is the same as saying that 3x plus 2, the stuff inside the absolute value, has to be less than or equal to 7 and greater than or equal to -7. Because this statement, this inequality right here, is saying that the quantity 3x plus 2 is at most 7 units away from 0 on the number line. And that's given by this compound inequality here. Now, once we have this compound inequality, we can go back and remember how we handled compound inequalities and try to solve for x. In this case, notice there's only one x term here, and it's already in the middle, so we'll be able to just solve for x in the middle of this inequality. We can subtract 2 from all sides, get -9. It's less than or equal to 3x, is less than or equal to 5. Divide everything by 3. Remember, whenever you multiply or divide by a negative number, we have to switch the order of the signs, but in this case, we're dividing by a positive number, so we keep the direction of the signs the same. We wind up with -3 is less than or equal to x is less than or equal to 5/3. And so here is our solution. We can sketch it out either on a number line, or we can give the interval notation, or both, depending on what's being asked for. So we're looking at all numbers x that lie between -3 and 5/3. So we're looking at all of these numbers in between. And then because these are both weak inequalities, if x actually is equal to -3, it will satisfy the inequality. So we include -3 in our answer. Similarly, we're going to include 5/3 in our answer because there's a weak inequality on the 5/3 side of this compound inequality. So our solution in interval notation is the interval from -3 to 5/3 with square brackets on both sides because both of those endpoints are included in the solution. If you are looking at an expression, or an inequality rather, where the absolute value isn't solved for already, then you need to get the absolute value on its own first. So let's take another example. Let's look at 2 times the absolute value of x plus 1 minus 3 has to be less than or equal to 5. We can't apply our rule yet about translating absolute value inequalities into compound inequalities because we need to get the absolute value by itself first. So first we solve for the absolute value term. So looking at that, we can add 3 to both sides. That'll give us 2 times the absolute value of x plus 1 is less than or equal to 8. Then we can divide both sides by 2. 2 is a positive number, so we don't have to change the direction of the inequality. And now we've gotten down to a point where we have the absolute value, which is less than or equal to the number 4. Now we can translate this into a compound inequality. This is the same as saying that -4 is less than or equal to x plus 1, which is less than or equal to 4. Again, this is a compound inequality where we can solve for x, and so we'll get -5 is less than or equal to x, which is less than or equal to 3. And so our solution This time we'll go ahead and go straight to the inequality. We want to say, what's the lower limit on x? What's the limit for how small x can be? And that's -5. X has to be greater than or equal to -5. So -5 is the smallest x can be. And because that's a less than or equal to symbol there, we'll use the square brackets to indicate that -5 actually is a solution. Similarly, the upper limit is 3. X can be at most 3 in order to satisfy this inequality, and therefore the upper limit to this inequality, or to this interval, is 3. So there's our solution set, all the numbers between -5 and 3. So that's how we handle inequalities involving an absolute value where the inequality is of the form the absolute value is less than something else, or less than or equal to something else. Let's talk about what we do when the inequality is greater than or equal to, because this is a little bit different. So what about something like the absolute value of x is greater than, we'll do greater than or equal to 3. Well, let's look at the number line again and think about what it means for the absolute value of x to be greater than or equal to 3. This means that the distance from x to 0 on the number line is at least 3. So this is saying that the absolute value of x has to be bigger than something. The absolute value of x can't be too small. The distance from x to 0 on the number line has to be at least 3. There are two different ways that that can happen. X can be far away from 0 on the right side of the number line or on the left side of the number line. So if we want to find all the numbers where the absolute value is at least 3, we can start at 0, move to the right, and then see that, okay, well, the first number, which has a distance of at least 3 from 0, is 3 itself. And then all the numbers bigger than that. So all of the numbers that are to the right of 3 are definitely included in the solution set to this inequality. And in this case, 3 is also, because we're looking at weak inequality, greater than or equal to. But of course, there's another way for this to happen. The absolute value of x could be bigger than 3 because x is less than -3. So the solution to an absolute value inequality that looks like this, where the absolute value has to be greater than or equal to some number, gives us two separate intervals that we need to work on. So we would express this as the collection of inequalities x is greater than or equal to 3, or x is less than or equal to -3. Notice that we're using the connector or between them now. When we worked with compound inequalities before, we were looking for an and statement. We wanted two inequalities to be true at once. This time, however, we're looking for a set of numbers where we just want the numbers to satisfy one of the two conditions. An element x is in this solution set, this green solution set, if x is greater than or equal to 3, or x is less than or equal to -3. So this gives us our rule, or a fact that we'll use. So if the absolute value of a is greater than k, then that means that that a is greater than k, or a is less than -k. And if the absolute value of a is greater than or equal to k, then that means that a is greater than or equal to k, or a is less than or equal to negative k. So notice what's going on here when we move from the absolute value inequality to the collection of inequalities. One of our new inequalities looks the same as the original one, just without the absolute value in it. But the other one, we've dropped the absolute value, we've changed the direction of the sign, and we've multiplied k by -1. So you need to do all of those things when translating it. If you write down your two inequalities and in your second one you forget to change the direction of the inequality, that's going to mess things up. If you forget to multiply your k, your value on the other side of the inequality, by a negative, that's going to mess you up also. So we have these two ways of translating a greater than or equal to inequality into a collection of ordinary inequalities. Now, if k is less than or equal to 0, we can get something, we can say something simpler than this, although it's a little different than before. If k is less than or equal to 0, the inequalities absolute value of a is greater than k and absolute value of a is greater than or equal to k have all real numbers as solutions. So before, when we were looking at the less than inequalities, I should specify here, I don't want k to be less than or equal to 0, just k less than 0. If k is less than 0, then the inequalities given here have all real numbers as solutions. And that's because an absolute value is always 0 or positive, which means that an absolute value is always greater than any negative number. So this is different than the other direction when we were looking at the less than inequalities, and this k, the number on the other side, was negative. The inequality had no solutions at all. Now it kind of has all the solutions. All real numbers are solutions. So let's do an example with this. So let's solve 2 plus the absolute value of 4x plus 5 is greater than 6. So once again, if you don't have your absolute value by itself on one side of the inequality, you need to do that first. You need to get it by itself. So let's go ahead and do that. We'll subtract 2 from both sides and get the absolute value of 4x plus 5 is greater than 4. So now we're going to translate this absolute value inequality into two separate inequalities. Because this is a greater than inequality, the absolute value is greater than some number, that means we're going to be turning it into an or statement. It's going to turn into one inequality or another inequality. The first inequality we get is the inequality that we get when we just drop the absolute values and keep everything else the same. For the other inequality, we need to drop the absolute values. We need to change the direction of the inequality. It was a greater than, now it's a less than. And we need to multiply the other side of the inequality by a -1. So we get that in order for the absolute value of 4x plus 5 to be greater than 4, that means that 4x plus 5 itself must be either greater than 4 itself or less than negative 4. Those are the two ways for 4x plus 5 to have an absolute value greater than 4. Now we can solve each of these inequalities on their own. We get 4x is greater than negative 1. We divide by 4, and we get x is greater than negative 1/4 on the one side, or we have 4x is less than negative 9 after we subtract 5 from both sides, and then we divide by 4, and we get x is less than negative 9/4. And remember, this is an or statement between them. And even if the problem doesn't explicitly ask you to sketch out the solution, it's often a very good idea to do so, just to make sure that you have everything correct in your own mind, and you can check that you've understood everything correctly. So we know that negative 1/4 and negative 9/4 are the two numbers that we have here. So first we have the inequality x is greater than negative 1/4. So that's going to be all the numbers greater than negative 1/4, and with a parenthesis boundary on it because we don't actually include negative 1/4 in our answer, because we need x to be strictly greater than it. For our other inequality, we want x to be less than negative 9/4. So we'll go to the negative 9/4, shade all the numbers to the left, and put a parenthesis there as well. So here's the sketch on the number line of our solution. And if we want an interval notation solution, which we usually will, we're going to write down these two these two intervals with a union symbol between them, like we talked about in an earlier video. So first we start with the left-hand interval. The left-hand interval goes from negative infinity, because it has no left boundary, up to negative 9/4 with a parenthesis, because negative 9/4 is not included. And then we have the interval from negative 1/4 to positive infinity, and then we connect those two with a union, meaning that our solution set is all of the points that lie in either of those two intervals. Now, the next thing to look at is what happens when we have a compound inequality involving an absolute value. Now, this really can be handled using all the techniques that we've seen before, but let's see an example of how that can go. So let's solve the inequality 0 is less than x minus 6, which is less than 10. So a compound inequality like this can be written as two separate inequalities, and that's what we're going to need to do, because we're going to need to use both of the rules that we have for dealing with inequalities separately, because one of our inequalities here involves an absolute value being greater than something, and one of them involves an absolute value being less than something, and we're going to need to handle each one of those. So the first thing we're going to do is we're going to break this up as 0 is less than the absolute value of x plus 6, and the absolute value of x minus 6 is less than 10. Keep track of whether you've got an and or an or relationship between the different inequalities that you're writing down, because often you'll have multiple inequalities that you're writing down when working in situations like this. So let's handle the left inequality first. Here we've got the absolute value of x plus 6 is greater than 0. Now here we've written it a little bit in the other direction than we were before, but remember that to say that the absolute value of something is greater than a number means that it has to be away from that number, either to the right or to the left, which means that this is going to turn into an OR statement, and we're going to get that 0 is less than x minus 6, or, and now we keep x minus 6 the same, we change the direction of the inequality, so the less than becomes a greater than, and we multiply the left-hand side by -1. So we've got a -0 there, although of course -0 is just 0. And so now we've got this OR inequality here. So let's keep that together. I like to put parentheses around the whole statement so that we understand that it's one of these two inequalities have to be true and the other inequality has to be true, which we haven't handled yet. Finishing this up, we can add 6 to both sides in both of our inequalities actually, and get 6 is less than x, or 6 is greater than x. Or in other words, x is greater than 6 or x is less than 6. This has an interpretation. This actually makes sense based on the inequality that we had up here. Let me take a quick aside for a second. Remember that the absolute value of the difference of two things can be interpreted as the distance between them. So this x minus 6 could be interpreted as the distance between x and 6. And so what this whole inequality is saying is that the distance between x and 6 is greater than 0. Well, really, the only thing that that means is that x can't actually be equal to 6. And if x is not equal to 6, then that means that x is either greater than 6 or less than 6, because one of those three relationships has to hold. So we get exactly that as we go through this process. However, if you recognize this sort of pattern, you can often quickly jump to saying, oh, well, the absolute value of x minus 6 is greater than 0. Well, that means that x is just not equal to 6. X has to be greater than 6 or less than 6. So I'll take as an aside here that this is just another way of saying that x is not equal to 6. All right, so that's simplified the left branch of our inequality down as far as it'll go. Let's do the right branch. Now, we've got here an absolute value is less than 10. Now, again, we think the absolute value is the distance away from 0. And if that's small, if that's forced to be less than some number like 10, that means that everything has to be kept together. It means we're looking for x minus 6 to lie between two things. So that's a way that we can help remember that this means that x minus 6 has to lie between -10 and 10. And so we can get this compound inequality. Simplifying this is, again, a matter of adding 6 to all sides. And so we get -4 is less than x is less than 16. So we've got a fairly complex set of inequalities here, but we can interpret them all as long as we are careful about it. So let's sketch out the numbers that are important to us. -4 and 16 are clearly going to be important to us based on the second branch that we did. And then 6 is important to us here. So let's sketch out what each of these inequalities are in a couple of different colors. So the left branch says that we're looking for all numbers that are greater than 6 or less than 6. So the way I'll write that down, and I'll do that above the graph here because I want to keep it, I'm not writing down my final answer yet. I just want to write that down. That's what this looks like. So this blue line with the hole at 6 indicates 6 is less than x or 6 is greater than x. Now let's use red for the other inequality, and this one's a compound inequality. It says that x has to be greater than -4 and less than 16. And we can sketch that out this way. So the blue line, or the blue set rather, has all the points in the real number line that satisfy the first inequality, the left inequality in the original compound inequality. And the red contains all of the points that satisfy the second of the original inequalities. Because we have and as the connector between them, the solution set is going to be all the numbers that lie in both the blue set and the red set together. So the solution is the overlap of the two sets. So we can see that that's going to be all the numbers from -4 up to 6, but not including 6. The blue line, the blue set has a hole at 6, doesn't include 6, and so we can't include 6 in our number either. So we get the numbers from -4 to 6, but not including 6, and then from 6 to 16, again, not including 6. So in this case, our solution is two intervals that happen to bump up right against each other. And this is what we commonly get when we have a 0 on the left-hand side of a compound inequality like this. This type of inequality, by the way, is very, very important in calculus. So if any of you are planning on going into science, mathematics, or will be taking calculus for whatever program you're in, this is the type of inequality that winds up being very, very important there. For us, though, we're just going to have the solution here, and we're going to write it in interval notation, again, as a union of two intervals. It's the union of the interval from -4 to 6 and the interval from 6 to 16. And so that's how we solve a compound inequality involving an absolute value. All right, the last topic that I want to talk about is what happens if we have an inequality involving two absolute values. And this one, honestly, is a little harder to give any sort of general strategy on. One of them, however, we can use, which is based on some of the more complex inequalities that we looked at back in the last chapter. So let's take as an example, let's say that we have 1 plus the absolute value of 2x plus 3 is greater than 4 plus the absolute value of x minus 6. So one thing that you can do here is you can find all places, or sorry, find all solutions to the equality. So just like when we were looking at inequalities, quadratic inequalities, and we just solved the equality and found points that way, we can do the same thing here. We can find all solutions to the equality and then use those to split up the real line and then test intervals. So let's see how that goes. So we're going to start with 1 plus the absolute value of 2x plus 3 equals 4 plus the absolute value of x minus 6. And this, as we saw last time, can take a little bit of work. We need to get one of the absolute values by itself. So we can subtract 1 from both sides to do that. Now if 2x plus 3 equals 3 plus the absolute value of x minus 6, absolute value 2x plus 3, this means that 2x plus 3 equals 3 plus the absolute value of x minus 6, or 2x plus 3 equals the opposite of 3 plus the absolute value of x minus 6. Just using our standard way of solving absolute value equations. So now we can try and solve this. We can subtract 3 from both sides, get 2x is equal to the absolute value of x minus 6. And now this can split up. We get 2x is equal to x minus 6, or negative 2x is equal to x minus 6. Once again, plugging these numbers into the, or changing the other side of the equality to a negative in order to get our two solutions to the absolute value equality. All right, so from here, if we solve these, which we can do quickly, we can get x is equal to, we can get x is equal to negative 6, or x is equal to 2 down here. And over, so that gives us the two solutions from our left branch of reasoning. And then we can take 2x plus 3 equals negative 3 minus the absolute value of x minus 6. Add 3, get 2x plus 6 is equal to negative absolute value of x minus 6. And then multiply both sides by negative 1 to get negative 2x minus 6 equals the absolute value of x minus 6. And so from here we can get negative 2x negative 2x minus 6 equals x minus 6, or 2x minus 6 equals x minus 6. In the second case, I've multiplied the negative 2x minus 6 by negative 1, because that's how we solve an absolute value equality. And then solving these down, in the first case, we get x equals 0, and in the other case, we get x equals 0 also. So in this case, we wound up with 3 possible solutions: x equals 6, x equals 2, and x equals 0. And the x equals 0 has been repeated. So now we do want to go and check to see whether they are in fact solutions to the equality, because we can get extraneous solutions here. So let's check. If we get x equals negative 6, then that tells us 1 plus 2, the absolute value, 2 times negative 6 plus 3 equals 4 plus the absolute value of negative 6 minus 6. And simplifying all this down, we get 1 plus the absolute value of negative 9 is 10. So 10 plus, and then negative 6 minus 6 is negative 12. Absolute value of that is 12. So we get 16, which is false. All right, so that means that x equals negative 6 was not a solution. How about x equals 2? We get 1 plus the absolute value of 2 times 2 plus 3 equals 4 plus the absolute value of 2 minus 6. That tells us that we've got 1 plus the absolute value of 7 is 8. And on the right-hand side, we get 4 plus the absolute value of negative 4 is 4 plus 4, which is 8. So that checks out. All right, so that means that 2 is an honest solution. And if you plug 0 in, you'll find that that's a solution also. I'm running out a little bit out of space here. But if you plug 2 in, you'll realize that you'll get 4 on both sides. Oh, I'm sorry. I misread that. X equals 0 is not a solution. If you plug 0 in, then you'll get 4 on the left, and you'll get 10 on the right. So that doesn't work. So in fact, this absolute value equation only has one solution. It only has the solution 2, which means that the intervals of the real number line can be, there are 2 of them split at the number 2, and on each of those intervals, either all numbers in that interval will be solutions to the inequality, or they will all not be. So, once again, we've got this equation. We have x equals 2 as our only solution to the equation 1 plus absolute value of 2x plus 3 equals 4 plus the absolute value of x minus 6. So we can go here, 0, and then 2 is the place where we're really splitting up the number line. In fact, I won't even indicate 0 right now. So now we're going to test the intervals. We have 2 intervals we're looking at here, from negative infinity to 2 and from 2 to infinity. So we're going to take numbers in each of these intervals, plug them into the original inequality, and see whether we get a true statement or not. So let's test the number x equals 0 from the first interval, because that's usually easy to work with. And we'll plug it into the original inequality. We get 1 plus the absolute value of 2 times 0 plus 3 is greater than 4 plus the absolute value of 0 minus 6. This will give 1 plus the absolute value of 3 is greater than 4 plus the absolute value of negative 6, which gives 1 plus 3 is greater than 4 plus 6, and this is false. 1 plus 3 is not greater than 4 plus 6, which means that the interval from negative infinity to 2 contains no solutions, because all of the numbers in this interval must either they are all solutions or none of them are solutions. And because we found some number in the interval that wasn't a solution, that means that none of the numbers in that interval are solutions. So let's check x equals 3. If we plug x equals 3 in, we get 1 plus 2 times 3 plus 3 is greater than 4 plus the absolute value of 3 minus 6. So this gives 1 plus, now 2 times 3 is 6, plus 3 is 9. And is that greater than 4 plus, now 3 minus 6 is negative 3. The absolute value of negative 3 is 3. So we get 10 is greater than 7, which is true. So we have that the interval from 2 to infinity contains solutions to our inequality. The interval from negative infinity to 2 does not, and 2 is not going to be included. It's not going to be included in our solution because it made the two sides of the inequality equal, and the inequality we're looking at is a strict inequality. We're looking only for places where the left-hand side is strictly greater than the right-hand side. So our solution is the interval from 2 to infinity. Though that is the set of all numbers that make our equation above true. And this is the most reliable way of solving inequalities involving multiple absolute values. They take quite a bit of time to work on. Fortunately, they don't show up terribly often in application.